actually doesn't work. Yeah, if you go to the chapter 6, the unit 1 stuff, chapter 6, chapter 7, first exam is right there, answer key is right here. So a couple of things that I want to point out. First couple were okay. One thing on number 2, these functions are given as functions of t. These answers should be functions of t, not x. You shouldn't change the variable. If that's given as a function of t, they should end up as functions of t. Some of the skills from college algebra that you need to know that were not present are basic graphing skills. You have to be able to graph e to the x instantaneously. You shouldn't even have to think. If you have to think about what the graph of e to the x looks like, what the graph of natural log of x looks like, x squared, those things, you have not done enough prep work for this exam. Those things should be absolute. You shouldn't even have to think about those. And if you do have to think about them, you need to go back and practice your graphing, because as you move through Calc 2 and get into Calc 3, you have to be able to graph or you can't do the math. Like if you graph it wrong, the chances of you setting it up right are close to 0%. So this is graphing the square root of x, the line y equals 1, and the line x equals 2. Like that part shouldn't even, you get 0 points for doing that, because that's like so basic. So make sure you can do your basic graphs. I saw some horrendous graphs. You've got to practice them, because it's just going to get worse. You've got to be able to graph. On number 4, let's talk about number 4. There was all sorts of funny business things on number 4. We even did that one, like almost exactly in the review session. Find the volume of the solid with a semicircular base of radius 4. You can set up your semicircle in lots of different ways. You can set it up vertically, or it does not matter how you set it up. I will set it up centered at the origin because that makes the equation easiest. You could have the equation be centered at 4, 0 or 0, 4 if you want to make it a little harder. You can. When you have circles, it's always easiest if you set them at the origin, if it makes sense. Sometimes it doesn't make sense, but in this case it's easy to set it at the origin. But the thing in the question, it says parallel to the diameter. Parallel to the diameter. So if you drew your circle or semicircle the way I drew it, this is parallel to there's only one diameter in a semicircle, right there. That is your integration element right there, parallel to the diameter. And we know that it's going to create a square that's going to stick right out of the board. Ooh, doesn't like that. It's going to stick right out of the board. The area of a square is the base side squared, base length squared. So if we want to find the length across here, we've got to do the right curve minus the left curve. So you have to solve the semicircle for x, and then you have to double that amount so that you get all the way across. And then the area of a square is that base side length squared. So you square the 2, square the square root, and then it's a pretty easy integration from 0 to 4. But those words mean something. Parallel to the diameter. There's not a lot of words in these questions, so pay attention to all the words. They're all important. Number 5. This is another one of those things. If it's not obvious to you at this point whether it should be a dx or a dy based on whether it's a disk or a washer, you have done a fraction of your job. That shouldn't even be a question at this point. If you are struggling to decide whether it should be dx or dy, you need to go spend 10 hours doing just these things, stuff based on the worksheet. That should be absolutely obvious by now, and if it's not, you're not doing enough work, and it's just going to get worse. That has to be obvious. When we say that the axis of rotation is horizontal, let's undo that. So like in this one, number 5, we're rotating around the line y equals 3. That is horizontal. And if we are going to build a washer, that means we are using dx. And if that's not totally obvious, you've got to go do more work because it has to be obvious. You know, if you have a horizontal axis of rotation and you choose a vertical element, you're going to create a disk or a washer depending on whether there's a gap or not. If it's parallel, that's dy. That's going to create a cylinder. Right? That has to become really, really obvious because these integration things like washers and disks, we're not going to do a ton of them as we go forward in this class, but they are coming, they're going to be there, and you certainly are going to see them in Calc 3 in a slightly more advanced format. So number 5 is a washer, outer radius squared minus inner radius squared. The outer radius is to the further curve, so it's going to be, and it's vertical, so it's upper minus lower. Anytime you do vertical, upper minus lower. Anytime you do horizontal, right minus left. Every time. No matter what. Let's see. So, blah, 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 blah. This rope one, the ADD part, the second D, distance, if you're setting it up so that it is like the problem is worded, where you're dropping the rope, if you're at a height of 10, how far does that move? If I'm at height 10 and I drop it, how far does it travel before it hits the ground? 10. Not 80 minus y. Right? It should just be y, not 80 minus y. But because it's symmetric, whether you winched it up, if you winched it up, you're doing the work. If you just drop it, then gravity's doing the work, but the work will be equivalent. So I didn't take off for that, but just in your mind, realize it should just be a y because you're dropping it. So if you're at height y and you drop it, it drops y units of length, y distance. And then we integrate 0 to 80. Let's see, this one, 10. 10 was the hardest one in terms of the algebra, but that's not where most people got screwed up. It was just the setup where most people got screwed up. So in 10, we are finding work done, ADD volume. ADD, for most part, no trouble. This thing, in number 10, what are the cross sections? What geometric shape are the cross sections? Circle. So more correctly, a disk, right? It's a disk. What is the area of a disk?
Pi r squared.
Stop!
Why did I write 2 pi r squared?
Some people thought it was 2 pi r squared. You weren't the only one that did 2 pi r squared. But the biggest mistake here, of course, you have to solve for x because you're measuring horizontal, and that's going to be your radius. That's the radius. And a lot of you got the 1/5 y plus 1 and then doubled it. The area of a circle, the area of a disk is pi r squared. It's not pi diameter squared. You don't double the radius and then square it. So that was the most common mistake, was doubling this. Because we're doing an area, area of a slice, which is the area of the cross section times dy. So that's what your pi r squared should look like there. But that one had the nastiest algebra for sure. And then down here, let me talk about this one for a moment. This is not in log form the way it sits. The way it sits on the question, it's not in log form. And so something needs to be done. I don't know why the formatting on the ones I printed out came out so screwy. The number 10 got printed on the prior page. I don't know why. Okay. But that is not log form. The derivative of the denominator is not the numerator. It's close, but you have to do something. You can say to yourself the derivative of the denominator is 2 sinh. So you could then multiply the top by 2 and divide the outside by 2 and multiply by half. That's fine. You could factor out the 2, which some people did, but for some reason, the algebra 1 skill of factoring was problematic. Factoring a 2 out of 2 terms there, how many times does 2 go into 1? Right? You've got to, if you pull the 2 out of there, you get a half. If you factor the 2 out, it has to factor out of the 1 also. Everyone agree? Please say yes.
Yes.
Right? So if you factor the 2 out, that's a totally fine approach. So there's 2 different looks that this answer could have. If you factored out the 2, so you had a half in front, then you would have a minus half here, and you would have natural log of cosh minus half. Right? If you do the multiply and divide by 2, then you'd have a natural log of 2 cosh minus 1. Yeah, don't do that. Okay, all right, look at the answer key. Let me know during break or after, wherever. If you have questions, you can email me, you can come to my office, you can come to the Math Center, and we can, if you have confusion on why you aren't understanding something, come and see me and I will help you. Stay after class, I will help you. Question? You enough?
No, well, I was going to ask you later, but this is a personal question.
Oh yeah, let's not ask personal questions.
Yeah,
right
that's
now.
why, yeah. That's why I said never mind. I was like,
Let's not do personal questions right now. We'll do personal questions later. All right, let's go to Chapter 8, Unit 2, Section 8.1. So Chapter 8 is all about mastering integration. Mastering integration is a good thing to do because calculus and physics is littered with integration. So if you can be a good integrator, you're gonna be a happy camper. Okay, so this table here has all of the basic integrals that you should already be familiar with. I forgot to bring my nice soft pen. I'm going to use this miserable pen. Perhaps the inverse trig functions aren't as familiar to you. You should have seen them nonetheless. There is a third inverse trig function up here somewhere. I don't even... 13. Oh, there, thank you. Oh, 11, 12, 13. They're in an order. Those three. So we are going to learn in the not too distant future a very strategic way to get to these inverses. At this stage of the game, you should be familiar that if you see a sum of squares or a difference of squares, that it probably is going to integrate to an inverse trig function of some sort. So at this point, you should just be able to use the table to get to an answer if you see an integrand that matches one of those three. The other ones, though, you should already have dialed. If you don't, note cards. Note cards every night. A great way to knock yourself out at night is to look at your math note cards. You will sleep like a baby. They will put you to sleep. But you'll also learn them really well. Okay, so make sure that all of those are familiar. And the first thing that we're going to look at are some different... First section, 8.1, is just sort of all these random little techniques for integration. So the first random technique, which we have done, a bunch of these we've actually already talked about, is when you have a power of 2 on sine or cosine. Not secant or cotangent or any of those other functions. Sine or cosine, we have to do power reduction. Power reduction is the only way to go. So power reduction is how we integrate these things. So let me do the first one, I'll let you do the second one. So if we have the integral of sine squared, we are going to first rewrite this. And now there's a couple of ways you can rewrite the identity. Usually I write it this way. So there's the first one. So when you power reduce, you increase the angle. So if you power reduce sine squared, you're reducing the power from a 2 down to a 1 on this cosine. That's cosine to the first power of the angle 2 theta. So we can factor the 1/2 all the way to the front, and we are just integrating this. All right. And then we integrate, and we've talked about the reverse chain rule already. The integral of theta is, the integral of 1 is theta. Integral of the trig function cosine is the trig function sine. The angle does not change, but then we have our reverse chain rule. We have to divide by the derivative of the angle. So don't forget reverse chain rule. And this was just an indefinite integral, so we're pretty much done. So we have 1/2 theta minus 1/4 sine of 2 theta plus c. All right, so there is how we would integrate sine squared.
Can we just leave the 1/2 in front?
You can, but generally factoring out of just 2 terms is kind of worthless.
Okay.
If you can't factor out of all the terms, it's kind of, there's no benefit to it. You know, it's like, I mean, it's like this, the classic, you know, boneheaded algebra thing that I see a lot is this. Like, you don't write this like that, right? Like if you're going to factor, the whole point is to factor it out of everything, so that you're turning things into a ooh, that's probably not the right thing to click. You want to if you can factor it out of everything, then you have the option to find zeros. And so yeah, we don't want to factor unless we can factor out of everything. But you could leave it like this too. You know, it's not wrong. All right, so you guys try this one. So cosine squared of 3 theta. Power reduce it and integrate. Power reduce. So remember, the power reduction identities are the same except for one's a minus, one's a plus. Otherwise, they're the same. And the power reduction that has the minus is sin. Sin is negative, usually. Unless you're a college student, I guess. College students like the sin. And when you do that power reduction, the function is still the same, right? But what happens to the angle? What does that angle become?
2 theta.
6 theta. So it's doubled. Just like we doubled the angle there, the angle went from theta to 2 theta. If the angle starts at 3 theta, then that gets doubled to 6 theta. Everyone okay with that? So same idea here. You should be factoring out that 1/2 in the denominator. And then hopefully no trouble here. Once again, the integral of the trig function cosine is the trig function sine. And then we deal with the angle by doing reverse chain rule. And again, normally you could leave it like that, but the preference would be to write it without that partially factored. Oh my gosh. All right, any questions?
So what if you have, pretty sure the answer is already, but what if you have like cosine cubed? Would you just go about it normally rather than?
So that's a good question. So if the power on cosine is higher than a 2,
Yes.
then we're going to learn a different technique in a couple of sections. We're going to look at when you have powers of sine and cosine and powers on tan and secant. Yeah.
What about powers in the hyperbolics?
Which we can do for fun.
Oh, well, we won't have to know how to do that.
No.
Okay, good.
Yeah, we won't see hyperbolics again, really.
Let's go.
So we don't have to know about integration with cosecant and secant, because you just said cosine tangent.
No, we're going to do powers of sine and cosine, powers of tangent and secant. But also, the other ones are going to just be a subset of that.
Oh,
Like
okay.
cosecant and cotangent will be parallel.
Okay.
We'll focus mostly on sine, cosine, secant, tangent, though. Okay, so RCR, next slide. We've already done this. This is just a quick review. Just remember that RCR, reverse chain rule, that is whenever you want to shortcut your substitution. So any problem that has substitution can be done with RCR if the substitution is linear. So because that substitution would be a linear substitution, we would let u be 3 minus 4x, and then we would take the derivative and get du is minus 4 dx. And then we would isolate the dx and write that as du divided by negative 4. And then we would come over here and say, okay, this is going to be e to the u. And dx is du over negative 4. The negative 4 in the denominator comes to the front. We integrate e to the u to itself, constant of integration, and then we do our back substitution. So if you were doing this problem with substitution, that's what you would do. All that work. But if you do it with reverse chain rule, the integral of an exponential is itself divided by the derivative of the exponent, and you're done. It's one step. Which is why being good at reverse chain rule is so important. Who wants to write down all those steps when it's really just immediate? It's instantaneous. Again, reverse chain rule only works when the substitution step is linear. But when it's linear, you should be able to just cut right to the chase. Part of being able to do well in math is to take advantage of some of these shortcuts. It's easy to say, oh, I don't want to learn another shortcut, I'll just do substitution, but it's just then all of a sudden it takes too much time. And if you're going to do it 1,000 times, why not learn to do it in the beginning? So these two, first thing that you look at is the angle here. You say, okay, that's linear. Here you look at the radicand. You look at what's under the radical. That would be these are the natural choices for substitution. What's in an angle, what's in a square root, what's in an exponent. It's always sort of what's buried inside. So try each of these. Write down, and these should be problems that you should be able to write down the answer immediately. It's one step. Maybe a second step if you have to combine some constants. So see if you can write those down. So as we've seen a bunch of times on the first one, the integral of cosine of sine, angle can't change when you integrate or differentiate. But then if you're integrating, you do the reverse chain rule, so you divide by the angle's derivative. And again, these are being highlighted because these are linear. Reverse chain rule is only going to work if your substitution is linear. All right, so see if you can get that second one. The second one is a little more work. Good.
1/6.
Wait, what did you say, Mad Dog?
The other one.
1/6?
I think so, yeah.
Okay. 1/6 what?
Well, 4x minus 1 to the 3 halves.
Okay, we'll see. Let's try it out.
Now I should.
Let's try it out. Okay, so it's, let's see. That could be it. I haven't done it yet. So it's 4x minus 1 to the half. You add 1, so you get 3 halves. You divide by 3 halves, which means multiply by 2/3. But then you have to do RCR, so you have to divide by 4. And so this is going to end up being very nice. Well done. Is there any piece of that you need more explanation on? So when you're using the power rule part, you add 1 to the exponent, so 1/2 plus 1 is 3 halves. Divide by 3 halves, which means multiply by 2/3. And then RCR, you divide by the derivative of the angle. So this in here, this division right here, that's your RCR. Divide by derivative of angle. All right, here's another random thing that is helpful. If you see negative exponents, this technique is called eliminate negative exponents. So if we see negative exponents within the integrand somewhere, before we try to do substitution, before we try anything else, step 1 is let's make the exponents positive. Let's get rid of the negative exponents. And is there a way that we can get rid of those negative exponents by multiplying by 1? So multiplying by 1 is always a clever technique to rewrite something. Multiplying by 1 doesn't change the value, it just changes the way it looks. Doesn't change the value though. What can I multiply numerator and denominator by to get rid of that negative exponent? E to the z. E to the z. So if we multiply the numerator and the denominator by e to the z, i.e. multiply by 1, e to the z over e to the z is 1. So then in the numerator, what's the numerator now?
E to the 2z squared.
No.
E to the 4z?
No.
3z?
Thank you. Back to algebra. Powers with the same base, you add the exponents. So multiplying 2 powers with base of e, add the exponents. Denominator, e to the 3z minus 4. Everyone agree? Can't believe that's happening again. So e to the z times e to the negative z is e to the 0. E to the 0 is 1. Now we have an integrand that is log form-ish. What do we need to multiply the numerator by so that it's in log form? Multiply the numerator by? What is the derivative of the denominator? 3e to the 3z, so the numerator is missing the 3. So if we multiply the numerator by 3, now the integral part's in log form, but we upset the balance. So to preserve the balance, we're going to divide by 3 on the outside, or multiply by a third, either way. Now it's in log form, though, so we have a 1/3 out in front, and this is log form. Log form, we get natural log of the absolute value of the denominator. Let's see. Do we need the absolute value bars there? Yes or no?
Yes.
Yes. If you plugged in z equals 0, e to the 0 is 1, 1 minus 4 is negative. So you can't take the log of a negative number, so you have to have the absolute value bars there. Must. Yep. Any other questions on that one before we go on? Yeah.
So anytime you do an integral and it's in log format, you have to include absolute value.
Yes.
Okay.
You can take them away if the denominator is always non-negative.
Okay.
But if the denominator can be negative, you have to leave them.
Okay.
Ari?
So it's just safe to just always leave them?
Sure. Yeah. Yeah. If you want to just be mindless about it, then just always put them in. But if you think about it and you realize that, oh, this is always non-negative, then you can take them away. You wouldn't be marked off if they were on there, though.
So would you recommend for taking more math classes and stuff in the future to recognize that?
Yes,
Okay.
definitely, definitely. Yeah, I mean, it's kind of like, you know, it's like this kind of thing. Like to a math person, is that how you write 1x? Right? It's disgusting. We write it like that,
I know somebody who writes that.
right? Putting the 1 in just feels, you know, like for you all have been doing math long enough, that's not how you write it anymore. It's that same idea.
Okay.
Would you
Yeah.
mark off for that? Not that we would do it, but would you mark
For
off
for doing that?
Yeah.
No, I wouldn't take off for it. I would just squirm. Like I saw some of you squirm. Because it just doesn't look right. It's like, don't do that. It just looks weird. Okay, so what do you think we can multiply top and bottom here by? I heard it. Somebody said y cubed. So if we look at the most negative exponent, so the biggest negative exponent, and we use that as our target, then this will wipe all the negative exponents out. Whoops, that's supposed to be a positive 3. It's going to wipe them all out instantaneously. So let's get rid of it. Let's start over. Yee, started looking ugly. So y cubed over y cubed. So that's our form of 1 that's going to reimagine the problem. So in the numerator, it's just y cubed now. And in the denominator, what are we going to have?
Y squared plus 1.
Y squared plus 1. Very good. Does everybody see that? That y cubed is being distributed. So this y cubed is going to hit that and hit that. So we have y to the 3 times y to the negative 1. Powers with the same base, add the exponents. And now we're going to learn another technique that's jammed inside here. What is it called when you have this kind of fraction? What kind of fraction is that?
Improper.
Improper. Right? When someone says it's a fraction of blah, 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 fraction of the cost. when we use the word fraction, we mean a proper fraction, which is less than 1 in value. Like 3/4 of something, that's a fraction of the something. 5/2 is improper because it's bigger than 1. If you multiply that by something, you're going to increase, right? So it's not intuitively a fraction, so we call it improper. There is a similar concept for rational expressions. That integrand is a rational expression, right? It's got a polynomial divided by a polynomial. Polynomial in the numerator has a higher power. The numerator has a higher power than the denominator. They don't use this word in the books, but it's analogous to what we just said. I would call that an improper rational expression because the numerator is larger. And in order to integrate something like this that's improper, it's top heavy, there's more y's up top than down below, you do long division. All the algebras, all those algebras that you did, all the maths. So we have to do long division. In order to integrate this, the best strategy is to rewrite the integrand by long division.
Is this also synthetic division, or is that different?
Synthetic division only works if you're dividing by something that is linear,
Oh,
just like for RCR. So this is going to be y cubed plus y. We will be subtracting that amount. So we have y cubed minus y cubed, which is 0. The y, that's why we chose this. Get rid of the y cubes. And then we have, up in here, we have 0 y's. If you have to, you can write it. So we have 0 y's minus 1 y. 0 minus 1 is -1. So we get that. And as soon as the power on this, whatever this term is here, as soon as that power is less than the power of the divisor, then we're good to go. Now we can rewrite it. So now we can go like this. This is going to be y is the quotient. And then we have minus y, I'll factor the minus to the front, divided by y squared plus 1. So same strategy that you do with mixed numbers, or with improper fractions, I should say. If you have something like 9/5, that's 1. That's called the quotient. Plus, it goes in once and you're left 4/5. That part is the remainder and that part is the divisor. So same idea. And with mixed numbers, you can end up writing it like that if you want, but same idea. The quotient is what you get when you, up here, it's this polynomial up here, it's that divides in originally, and then the remainder is this thing down there, and then you divide it by the divisor. So same old thing, although it might have been a minute. Now that's integrable. That is integrable. This is y squared divided by 2. And let's do the second part. Let's break it apart into 2 pieces just to make sure that we're 100% on how to integrate the second part. What form is that second integral in? It's almost in log form. We need to multiply by 2. So we're going to come up here and say it's not in log form yet. Now it is. Now that integral's in log form, the derivative of the denominator is the numerator. But if you do that, you have to do this to preserve the equality. Now it's integrable though. You could have used substitution if you wanted and made like 6 more steps. If you're trying to get your steps in, you could do substitution. Now I see that this denominator is definitely never negative, So I'm not going to even put the absolute value bars.
You can factor out 1/2, right?
But the half, if we factored it out, it would only come out of the first two terms, not the c, so we would normally not.
Plus c over 2.
Don't do it. But it wouldn't be c over 2, it would be... If you were going to factor out the half, including from the c, it would not, what would the c term be? If you factored out a half? 2c. 2c. Okay. So that's another, so we've had a couple of techniques so far. On this slide, getting rid of negative exponents. So we got rid of negative exponents, but now we've also seen this other thing, if you have a fraction that's top heavy, do long division.
Can you explain adding to
Adding 2 or multiplying by 2?
multiplying by 2?
Multiplying by 2? So what is the denominator's derivative?
2y.
2y. And so the numerator was only y to begin with, and we know that we could change the numerator to 2y if we multiplied it by 2. And so we multiply it by 2, but if you multiply by 2, you have to divide by 2 to preserve the equality. But doing the multiplication by 2 in the numerator gives you log form. Log form is always when the denominator's derivative is exactly the numerator. So we're trying to create the derivative of the denominator in the numerator. That's a fake smile. Austin?
So technically speaking, you're multiplying by 1.
Yes.
Keeping the top 2 and taking out the extra 1/2.
Yeah, that's right. We're multiplying the top and the bottom by 2, so we are multiplying by 1. It's just that the 2 in the denominator, we're going to factor it out. Yeah, that's right.
Could you explain the y squared?
Right here?
Yeah.
That's from integrating this y.
Oh.
Right, so this integral symbol is going to integrate both this term and that term. So I integrated that term and then integrated this one second.
Okay.
Yeah, make sense?
Yeah.
The housing was broken.
Question?
And this is going to be a history question,
That's
that's
okay.
not conducive to class, so.
Oh, we'll talk about later then. All right, so next technique, fraction splitting. Notice that this denominator here has 2 terms. The numerator has 1 term. There's no way to split that fraction. If you have a fraction where the denominator has 2 terms, there's no way to split it into 2 fractions. Right? You can't just like separate it. Well, if the denominator is 1 term and the numerator is multi-termed, you can split it. So this is a super common technique. We are going to turn this into the integral of 3x divided by the square root of 4 minus x squared dx, separated into 2 completely separate integrals. Okay, so that's called fraction splitting. Split the fraction. So it only works if the denominator is a singleton, if it's 1 term. So that denominator is a square root. It can be divided into both. Now, the integral on the right, we see this difference of squares tucked inside this root. And that difference of squares, whenever we see a difference of squares, we should be thinking inverse trig functions. And we're going to see a lot of that later. Ooh. Touchy.
You like leaving the dx in the numerator as 1.
When you're doing math, I would prefer if we just, like this looks better.
Yeah.
It's like the integral with the derivative, it's sort of like a vice, and it's integrating what's inside of it. But when they're, like when you're trying to save space, when you're making books and things, and this is just what they do. So it's, it's kind of like the angle thing. When we see tangent of 2 theta, we really should be doing that, but we don't. It's one of those things that it's a shortcut that we do just to save space. Yeah. I agree with you, though.
Like, I understand why it makes sense, it just looks weird.
I know. I agree. I totally agree. We got to get used to weird. Okay, so this is inverse trig, inverse sine in particular. So that's an immediate antiderivative. We just follow the rule from that integration statement above. How about the first integral? What technique do you think we could employ for that first one?
I like a 1 with the square roots.
Rationalize the denominator?
Yeah, that.
Rationalizing the denominator is going to make it more complicated. Because then you're going to have 2 terms in the bottom. In the numerator, you're going to have a product. You would have 3x times the square root. Gage? Substitution. Substitution is used when you have square roots and you have trig functions. You're looking at the inside of a root, the inside of an angle, the inside of an exponent. So substitution is always something to consider if you see a square root. And the natural sub is to let u be whatever's in the square root, in the angle, in the exponent. And here we see that, oh, okay, that's quadratic. Its derivative is linear, which is what the numerator is. So that's going to match pretty nicely. So let's go ahead and do that. Let's make a little more space here. So if we let u be 4 minus x squared, so let's focus on terminology for a minute. We always say at this stage, take the derivative. And it's true, that's what we're doing. But more correctly, we're taking the differential of both sides. If we were going to call it the derivative, really there would be an intermediate step here. When you take a derivative, you always have to indicate what you're taking it with respect to, and you would write this. This is sort of a missing step that no one ever puts in these problems for substitution. And then you multiply both sides by the dx. So this first one, that's truly, if someone said take the derivative, that's really what it should look like. But in the context of integration, that's how we write it, because that's what allows us to do the substitution. But technically here, this u, this is the differential of u, and this over here is the differential of this side with respect to x. Not super important to master the terminology quite yet, but just keep in mind that this is the derivative, and then we multiply the dx to the other side for the substitution.
Quite yet in perspective to this class or future class?
Future classes. Yeah, futures. The future. Okay, so now here, when I look up at this integrand, I see the x and I see the dx. So I see that down here in this substitution step. So I want to unravel that -2. I'm going to move that -2 to the left-hand side so that I can isolate the x dx. The x dx will then replace that x dx up inside the integrand. Okay, so we have the integral of, we let u be 4 minus x squared. So this is u to the 1/2 in the denominator right there, u to the half. I'm going to move it to the numerator, so it's going to be u to the -1/2. Now, this 3, that's going to just factor out to the front. It's a multiplicative constant, so it just comes to the front. So 3. Now, so we've taken care of the 3, we've taken care of the root. Now the x dx, the yellow part, x dx is du over -2. So we put du over -2, and it's just fine to put the over -2 part, put it out in front with the other constant. And so there is the substitution. Any mental anguish or drama with that substitution? Make sense? Question?
For that last step, could you also have multiplied both sides by 3 and done it that way?
Multiply both sides by 3 down here?
Yeah.
100%. So if you look at some of those help me solve this things in my math lab, and if you look at answer keys where they show you the steps, sometimes you are not going to know what the heck they are doing, but what they are doing is what you just suggested. Instead of doing it like I just did, where I said, okay, I see clearly that I can make x dx, I'll just factor this 3 out, and then I'll replace the x dx with what it is, the du over negative 2. What a lot of answer keys will do is try to match that numerator exactly, which is not always easy. In this case, it's easy. All we would have to do is multiply both sides right here by 3. And so then you could replace 3x dx with 3 du over negative 2. Definitely. You will see when you start looking at some of those answer keys, though, in my math lab, it's like, what in the world are they doing? And that's what they're trying to do. They're trying to create an exact match. But you don't need an exact match, because you can just factor the 3 out. You can just factor out the 3 if it's hard to make an exact match. You don't have to. That's a great question. Okay, so then let's focus on the inverse sine. So here, what is A down here? 2. So this is going to be inverse sine of x divided by 2, and then plus c. Okay, so now let's complete the substitution step here. So we have -3/2, leave a little space there. Yep.
If this was a definite integral for the second step, should we keep that in terms of taking antiderivative so at the end we can combine, like, say, the bounds of 2 to 3?
Yeah.
Okay.
Yes. Yeah, that's definitely. If it was a definite integral, then we want to time it so that everything's being integrated at the same moment.
Okay.
Yeah.
If the 4 was like a 5 or like a not perfect square number, would you just use the square root?
Yes. Good question.
Yeah.
So if this was a 5 right there, 5 minus x squared, this would be x divided by square root of 5. Exactly. Yeah. So here we're going to add 1 to the exponent, and we're going to get u to the positive 1/2. Dividing by positive 1/2 is multiplying by 2. And then inverse sine of x halves plus c. And then our final step is our back substitution for the u. So we're going to have -3 square root 4 minus x squared. And we get that. Oh, so there is our antiderivative. Oh, trapezoid. Trapezoid. All right, any questions on that? Good? Yeah, all right.
So only ever once.
One C.
I did it right.
So if you're thinking about integrating if you break the integral into 2 separate integrals, you could think, okay, they're creating 2 separate C's, but we always merge them together. It's like a recycle bin. Pile them together. All right, let's go ahead and take our 10-minute break, and then we will do some more. Let me leave that up there in case anyone's still trying to figure it out. And if you have questions, let me know. Pause. All right, so this is another one where we notice that it's top heavy. The denominator has a higher power than the numerator has a higher power than the denominator. So we're going to use long division. But the first thing we want to do is get the order similar. So when you're doing long division, you want everything written from highest power to lowest power, or it's going to get turned into a total disaster. So I'm going to factor a -1 out of the numerator. So now you recognize that it's improper. Now we're going to do our long division. And when we do the long division, we're going to take x squared plus 4. We're going to divide it into x to the 4th minus 6. I'm going to leave some space there just in case we need placeholders, some zeros. How many times does x squared go into x to the 4th?
2.
So we're going to think about x squared times x squared, giving x to the 4th. So this will be an x squared. And that's going to give us x to the 4th plus 4x squared. And then remember that we are subtracting.
Wait, where did the 4x squared come from?
Why is that happening? Say again.
Where's the 4x squared come from again?
So we multiply this x squared by each of these. So x squared times x squared is x to the 4th. X squared times 4 is 4x squared. And now we're going to subtract. So we're going to subtract off that. So if you want to, up here, you can think of putting in a 0x squared. So then we have x to the 4th minus x to the 4th, which is 0. We have 0 minus 4, which is negative 4x squared minus 6. And we are not done yet because the powers are matching. The powers in that remainder area has to be less than the power of the divisor. So what do we put next here? Negative 4, because we're trying to multiply by whatever's necessary to match this negative 4x squared down here. We want to match that negative 4x squared. So it's x squared times negative 4 will match it. So that'll be negative 4x squared minus 16. And now we're subtracting all of that off. So if we're subtracting all of that off, we're going to get 0, but then we're going to get negative 6 minus a minus is plus 10. So that's the remainder. So that part's called the remainder down there. Remainder. This part up here is called the quotient. And then the other thing is called the divisor. Okay, so now we have it rewritten. So this becomes negative, I guess we'll just have the integral symbol. So x squared minus 4 is the quotient. So we start there. And then we put the remainder over the divisor. So 10 over x squared plus 4 dx. So quotient plus remainder over divisor.
Can factors like an x minus 2 out maybe?
Well, we can integrate now. These we can integrate term by term. So we'll integrate term by term. So we have a minus all the way out in front, and then we're going to integrate. We're going to get x cubed divided by 3 minus 4x plus, this is an inverse tangent. And if you look at our basic inverse tangent thing, we're going to have an x over a on the inside, just like we had for inverse sine, an x over a. But notice on the outside of arctan, there's a 1 over a, whereas on sine, there is no 1 over a. So we have to figure out what a is, and then there's going to be a 1 over a multiplier out in the front. So what is a here? 2. So we've got the 10 from the numerator. And then we're going to have the over a, so over 2 inverse tangent of x divided by a, and then plus c. So final answer, we can just do a tiny bit of simplification. Minus x cubed over 3 plus 4x minus 5 arctan x over 2 plus c. All right, any part of that you have a question on? Our next one-off technique, completing the square. Another one of those awesome algebra techniques that you haven't done in a while. Wow, a little finicky.
Like you said, the HDMI cable helped with that.
They replaced them all. They replaced all the HDMI cables a couple weeks ago, thinking that that was the main culprit.
IT's really happy with you all right now.
Yeah, math and IT, we have way too many conversations. So this polynomial in the denominator, not factorable. Like if it was a perfect square, we would be able to factor it and maybe do something. It's not factorable. So what do? We make it factorable by completing the square. And when we complete the square, we are looking at the first two terms. And what would we need to add? What constant do we need to make this a perfect square trinomial?
16.
So you take the middle term's coefficient, divide it by 2, and square. So we would take that, divide by 2, and square, and we'd get 4. So now, if we had a 4, then this would be a perfect square trinomial, and it would factor.
You're right.
So you take the coefficient, divide it by 2, and square it. So we need a 4. So what I'm going to do is borrow a 4 from the 8. So what we're going to do is take this 8 and bust it apart into 4 plus 4 so that this part is a perfect square. All right, so let's factor that. So in the denominator, we're going to have x plus 2 quantity squared plus 4 dx. Okay, so the denominator has kind of that inverse tangent vibe going right now, something squared plus 4. So what we're going to do, we have two choices here. The most straightforward choice is probably to just do a u substitution where we get rid of this x plus 2 so that it looks more like, u squared plus 4 instead of x plus 2 squared plus 4. It'll be a little easier. So let's do that. That's a pretty natural thing to see. So let's say if we just get rid of that x plus 2, and we see pretty quickly that du is going to be equal to dx. There's one little wrinkle here. And let's see what it is. So in the denominator, we now have u squared plus 4. So that's a very nice looking arctangent business. And du and dx are the same. So du. But what does the numerator become? So the du and the dx match, but the numerator becomes
U minus 2.
u minus 2. So we look right here, and we isolate x. If we isolate x here, x is u minus 2. And that's what we're going to do. So u minus 2. Okay, now how about limits of integration? 2 and 4. So when x is 0, so we're plugging in right over here. When x is 0, u is 2. And when x is 2, u is 4. We got that. And now what strategy do we use?
Long division?
Not long division because the power in the bottom is big now.
Oh, yeah.
So long division is always when it's top heavy, and the denominator will divide into it. So no long division. We have used this technique today already.
Split it.
Split the fraction. So split the fraction. So if we split the fraction, we're going to have 2 to 4 u over u squared plus 4 du minus 2 times the integral from 2 to 4 of du over u squared plus 4. So split the fraction, factor out the negative 2. And what form is that first integral in? Log form. We have to do a little massaging. We have to put a 2 there and a 1/2 out there. Now it's truly in log form. And what form is the second integral?
Inverse tangent.
Inverse tangent. So that's an inverse tangent. So we will have 1/2 natural log, absolute value. We don't need absolute value. That's always positive. U squared plus 4. Minus 2. And then let's remember for arctangent, we see that A is 2. So we're going to have a 1/8 out in, a 1 over A out in front. So that's a 1 over 2 out in front. So it's going to be a division by 2 out in front. And then it's going to be arctangent of x over a, so that's arctangent of x divided by 2. And then all of this is being evaluated on the interval 2 to 4. And I have the wrong letter there. It should be a u, not an x. It should be a u. All right, we're almost there. So now we just have to substitute our limits of integration. So if we plug in the 4 first, we're going to have a 1/2 natural log. 4 squared, 4 times 4, 16. So we get natural log of 20 minus inverse tangent of 2. And then we subtract off the antiderivative evaluated at 2. We're going to subtract off 1/2 natural log. 2 squared is 4. 4 plus 4 is 8. Minus a minus becomes plus inverse tangent of 1. All right, so before we do some trivial simplification, any questions up to that moment?
You said there's 2 ways to solve this, and this is just the first.
This is the way that the more normal way to do it. There's a clever way that it's not much faster, but
Oh, okay.
we don't need to talk about it. So then let's go ahead and do the one, let's combine the log pieces. So you remember your log properties?
Should be natural log of 20 over natural log of 8.
Natural
Natural log of 20 over 8.
100%. Yeah. So natural log of 20/8, 20 over 8. But we can reduce that, right? We can divide a 4 out of each. So it's 20 divided by 8, which reduces to 5/2, 20 over 8. And then minus arctan of 2, that's not a special value. But what is arctan of 1? What is the angle on the right side of the unit circle that has a tangent of 1? Pi over 4. Pi divided by 4. So that would be our final.
This might be a goofy question, but are we assuming we stay in radians the entire time of this class?
Yeah. Yeah, you need to be in radians. I don't know if it was made clear in calculus, but when you take the derivative of sine, it's cosine, only if you're in radians. If you're not in radians, then there's a conversion that has to happen.
180 over pi sine.
Yeah, we don't want to do that stuff. No, 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 no. Yeah, so we're always going to be in rads.
Okay.
Rads.
So you don't simplify the inverse tangent.
It can't be simplified. It's an irrational number. So the only specific values we know for inverse tangent come from the unit circle. So we could simplify inverse tan of 1. We could simplify inverse tan of root 3. We could simplify inverse tan of root 3 over 3. But those are about it. So.
Because it's bounded between -1 and 1, right?
Well, inverse tangents values, inverse tangent's always an angle between negative pi over 2 and pi over 2. The number that goes in inverse tangent can be anything, because the function looks like this. So you can, the domain is all reals, but the angle is somewhere between minus pi over 2 and positive pi over 2. Oh, that worked.
So we had
Some things work and some
problem
things
that was dealing with degrees and with trigonometry, we have to convert it to radians to take the derivative properly, and then we convert it and back to degrees.
Yeah, yes,
Okay.
technically, yes.
Technically, okay.
Yes, yes. All right, so here's another one where we're going to use something called conjugate multiplication. And we know that our Pythagorean identities all involve squares. Sine squared plus cosine squared equals 1. Tan squared plus 1 is secant squared. Right? They're all involving squares. So there's no replacement of this denominator with a trig sub right now, with some sort of trigonometric substitution. So what we're going to do, if we multiply by the conjugate here, so 1 plus cosecant of theta, what will happen will be a couple of good things. A couple of good things are going to happen here. So first off, the numerator will be this. And the good things are going to be focused on the denominator. We have 1 minus cosecant squared of theta. That can be rewritten as a single trig function. And this is good because then the denominator is a singleton. And singletons can be distributed into the numerator. When the denominator is multi-termed, that's usually a problem. You usually would love to rewrite the denominator as a single term because then you can fraction split. So 1 minus cosecant squared, what does that equal to? If you can't remember off the top of your head, just go to your Pythagorean identity, write it down like that. What do you divide everything by to get to cosecants and cotangents? Divide by? Haven't heard it yet.
Cosine?
Nope. If you divide everything by sine squared, you get the identity, right? Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And 1 divided by sine squared? Cosecant squared. So this is 1 minus cosecant squared. So if we move the cosecant squared to the left, then we have to move the cotangent squared to the right. So 1 minus cosecant squared is minus cotangent squared. And again, the good thing is that we can now fraction split. And I'm going to factor that minus sign out to the front. So we're sitting at that position now. Okay, so let's split the fractions. So we're going to have minus integral. So 1 divided by cotangent. Isn't that tangent? 1 divided by cotangent is tan. And then that one, cosecant divided by cotangent. Okay, let's see. Let's go to sines and cosines. If we go to sines and cosines, it'll be easier. So cosecant is 1 over sine, and then dividing by cotangent. So cotangent is cosine over sine, so if we divide by cotangent, it's the same as multiplying by tangent, so it's going to be sine over cosine.
That cotangent squared.
Oh, shoot, thank you. It's cotan squared. Cotan squared. Is that what you were going to say, Ari?
Yeah.
Thank you. Thank you. Cotan squared. We're still splitting the fraction, though. Oh, come on, stop it. Okay, we're still splitting the fraction. That's cotan squared. So instead of tangent, what is this then? 1 divided by cotan squared? It's going to be tangent squared. And we're going to do the same thing that we were talking about. 1 over sine, but what is cotangent squared if we write it as a fraction with sines and cosines? So we're going to square it, so it's going to be sine squared of theta over cosine squared of theta. D theta. All right. So then, tangent squared. We don't know the antiderivative for tangent squared, but we can use a Pythagorean identity to rewrite that. We can rewrite tan squared as secant squared minus 1. And secant squared does have an antiderivative. The derivative of tangent is secant squared, so the integral of secant squared is tangent. So we can use our Pythagorean identity there, and then here we're going to cancel out one sine. So we're going to have this. Let me point something out with this identity that I just used here. Here is a very, very good thing to have in your toolbox. The visualization for this identity is so helpful. And if you haven't seen this before, this is a really good thing to just have in your mind. So if this angle here is tangent, and this is a unit circle, so that point right there is 1, 0. It's a unit circle. You already know that if you looked at this point on the unit circle, that the coordinates of that point would be cosine, sine. You already know that. Well, it turns out that if you extend the terminal ray through the unit circle until you're vertical above 1, 0, this vertical is going to be tangent, and this hypotenuse is going to be secant. So there is the right triangle that shows us this identity. Tan squared plus 1 is secant squared, or secant squared minus 1 is tangent squared. So if you have that visual in your mind, it's really easy to deal with the tangent and secant identity. And we are going to use that identity a ton, so I think that's a really good thing to have in your mind. So it also gives you a really intuitive sense for how tangent and secant change together as theta gets closer to pi over 2. As theta gets closer to pi over 2, this vertical side gets bigger, the hypotenuse gets bigger, but notice that secant is always bigger than tangent because secant is the hypotenuse. So you can kind of see that. And you can see as theta goes to 0, tangent's going to 0 and secant's going to, As that theta rotates towards 0, what is secant rotating towards? 1. Right? That hypotenuse is shrinking down to 1. Tangent shrinking to 0. Now, do you see why tangent is that side there? Well, here's why. So tangent is that side. If you look at this little triangle here, you already just told me that you know that this is sine and this is cosine. Well, the red triangle and the blue triangle are similar. Similar triangles have corresponding ratios that are equal. What is the rise over the run for the little red triangle? Tangent, sine over cosine. That means that the rise over the run has to be tangent for the blue triangle. If the run is 1, the rise has to be tangent, because these triangles are similar. So rise over run has to match rise over run. So if this is equal to tangent, if the rise over the run is tangent there, the rise over the run has to be tangent there. And since the run is 1, the numerator has to be tangent. The rise has to be tangent. So that's a good triangle to have in your mind. There's a similar one for cosecant and cotangent. Okay, so let's integrate. So we have this minus out in front, which we'll maybe distribute later. Singe.
I was saying I like the hyperbole.
We love the hyperbolics. So what's the integral of secant squared? Tangent, because derivative of tangent is secant squared. Integral of 1 is just theta. What technique are we going to use to integrate this sine and cosine squared thing? Substitution. Let's do it right here. We're going to let u be cosine, and then du. So I'm letting u be cosine because it's got the higher power here. So this will be replaced with a u squared, and its derivative is essentially the numerator. The derivative is minus sine of theta d theta. So down here, we're going to end up with plus integral. We have u to the negative 2, because that u's in the denominator. And then sine of theta d theta is negative du. So that's going to put a negative in front of this integral and a du. So we'd have that. And I haven't put in a plus c yet for this. We integrated part of it. We know that there's a plus c coming, so we can wait. There's still a plus c that can, that's going to be introduced. So we don't have to put in that plus c right away. So we end up, if we distribute this minus sign, we get minus tangent of theta plus theta plus, that minus times that minus is plus. But then we integrate this and we get u to the negative 1 divided by negative 1. And there's our constant of integration. And the last step is to do back sub. So we're going to have negative tan plus theta minus 1 over u. U is cosine. What's 1 over cosine? So yeah, we have that secant getting replaced with 1 over cosine gets replaced with secant. Lo and behold. Okay, so that's conjugate. So if you see a trig function that's not, like, especially one of the alternate trig functions, like a cosecant, a secant, or tan or cotan, if it's not squared, you've got this situation. You can sort of force it to be one term by doing a conjugate multiplication.
And this is the quickest way to do this?
Yeah.
Okay.
Yeah, good question. All right.
So when you have a constant across an interval, and then you split that interval, how does that constant translate to the intervals?
We're talking about this constant here.
Oh, no, I mean the starting negative.
Say that once again, starting,
Negative,
where am I at?
the right side above the triangle.
The negative further.
That, when we're, that negative there?
Yeah.
And did you say, how does it, where does it go?
Yeah, after the integral splits into two.
So then it's got to distribute. So I'm just going to leave it all the way out in front. So it's just acting like a multiple of -1 in front of everything. And so then here I decided to push it in. So I pushed it in there to make that negative, pushed it here to make that positive. This negative and that negative combine to make a plus. But then when we do this integration here, then we introduce another minus. So then it goes back to negative again. See it? So it's just a bunch of negatives being combined into a new negative. An odd number of negatives make a negative. Odd number. All right, let's try this one.
Oh my gosh.
So totally random. Got a square root of a square root. So you all try this as your substitution and see if you can make it work. While I go fill my water bottle up. A root of a root. A root of a root.
If it works, our rest is. I got the last one. No, it's not. Either works. What if it does? Well, here's so close. What is it?
Circular substitution. X negative.
Wait. Oh, yeah.
Any success?
Yes.
Yes, success.
No, it's not success.
Not success.
It's a guess. It's an educated guess.
Educated guess. So first thing when we do this derivative here, if we're going to use that for our u, the derivative here is going to be 1/2 x to the minus 1/2 times dx. So this is going to be du equals 1/2 root x dx. Does everybody follow that part?
Yep.
Okay, so let's see. So this is going to be the integral of u. So that part's, let's see, we said that was u, so it's a square root of u, so u to the half. Then we have dx. So if we isolate dx over here, dx is going to be 2 root x du. Okay. Now, that's what we want to put right here. But we know that we have to have only u in there. So what we do is look back to here, and root x, if we isolate root x, that's going to be u minus 1. So this is going to be 2 times u minus 1 du. Everyone see that? So this root x here gets replaced right there with u minus 1. Now we have what we need. So 2 times u minus 1 du. Limits of integration, when x is 0, u is 1. And when x is 1, u is 2. So there is our substitution. All right, so this then becomes 2 times the integral from 1 to 2, u to the 3/2 minus u to the 1/2 du. So then we get 2 times u to the 5/2 times 2/5. Try to get lucky. And then minus u to the 3/2 times 2/3 from 1 to 2. Plug in the 2, and then plug in the 1 and take the difference. When we plug in a 2, this is square root of 2. Square root of 2 5 times. Square root of 2 5 times is going to be 2 times 2 times root 2, which is 4 root 2. We have 2 times 2/5 4 root 2 minus 2/3. Root 2 here 3 times is 2 root 2. And then we subtract off everything evaluated at 1, so we're going to get minus 2/5 plus 2/3. All times 2. All that stuff times 2. So we should be able to combine some things in here. I don't feel like dealing with it right now. I'll just write etc. We could combine these two terms, we combine those two terms, and we could distribute the 2. Or leave the 2. Yeah?
Can you do it to settle an argument?
Yes! We can do that. We can we can try to solve an argument here.
I want you to be right.
Okay, so 2 on the outside. So I'm going to treat this as 8 root 2 over 5. And I'm going to pull these root 2's into minus 4 root 2 over 3. And then here, we're going to have negative 6 plus 10, so 4/15. So if we get a common denominator of 15 there, everyone agree with that? Negative 6 and positive 10. 10 minus 6 is 4. So then here, we're going to end up with 2 multiplied by, we need a common denominator of 15 again, so it's going to be 24 minus 20. 24 minus 20 is 4. So we're going to have 4 root 2 over 15. Plus 4 over 15. And if we do the whole factoring thing, we're going to end up with 8/15 root 2 plus 1.
That's definitely what I got.
So if you gave us this question, you want us to go all the way to that last part?
I would, if you're simplifying it all the way, that's where you'd be. That's where you would get to.
Do you want us to simplify that?
I'm not going to give you one that kind of
Oh,
weird.
okay.
That's a little weirder than what we would do on a test. But it is just algebra. You should be able to muscle your way through that. Okay, so here's a weird problem. This is, we don't use the identity in the traditional way. So I say, think of a power reduction identity backwards. And if you think of the power reduction identity for cosine, you know that cosine squared of x is 1 plus cosine of 2x divided by 2. And that looks a heck of a lot like what we see inside the integrand, or the radicand, inside that radical there. So if we multiply both sides here by 2, what we see is that we have a match. We have a match for the inside of the root. Whoa. So the inside of the root can become 2 cosine squared of x. And then what's the square root of cosine squared?
Cosine,
Always?
plus or minus cosine.
Is the square root of cosine squared always cosine?
Absolute value.
What is the square root of x squared? Depends, right? This is actually absolute value of x. It's equal to x if x is positive or 0, and it's negative x if x is negative. Everyone agree? Square root of x squared is absolute x. Because if x is a positive number, then yeah, fine. Then square root of x squared is x if x is positive. But if x is negative, the square root of x squared can never be negative. So if x is a negative number, the answer would be negative x. So cosines, the square root of cosine squared is cosine as long as the cosine is positive. Is cosine positive on the interval 0 to pi halves? Yes, cosine is positive on the right side of the unit circle. So in this case, we can say that the square root of cosine squared is cosine. But it is not always true. In general, the square root of a square is the absolute value of the base. In general. Okay, so then we integrate cosine and get sine on this interval, 0 to pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. So we end up with just the square root of 2. Square root of 2. All right, so there's 8.1, a bunch of random techniques that you can only sort of get used to by doing a ton of homework. Does everybody know in my math lab that once you've done an assignment, like after the due date's reached, you can go back in and work problems as many times as you want if you go to the review button? That's a helpful way to go in and do extra practice. All right, new technique. You've all heard of it. Integration by parts, known on the streets as ultraviolet voodoo. Ultraviolet voodoo. So integration by parts is, at its root, a way to integrate a product. So one of its primary uses is as the reverse product rule. It allows us to integrate a product. It can be used for a ton of other problems, but at its core, it's best used, it's the best solution for things like this. Oh, there's the integral of a product. There's the integral of a product. It's really good for things like that, integrals of products. It can do other things, for sure, but that is the core integrating of products. This thing right here is a product. right? That's x multiplied by 1 over square root of x plus 1. That's the product. There's product. Yeah.
We could have used ultraviolet voodoo for this problem back here in this step.
Oh,
Never mind.
it'd be really, really hard for that one. So here's what ultraviolet voodoo says. It's best to do some problems because it's kind of abstract, but the idea is that think of each of these individual things. U, each of these factors, U, dv, v, du. Think of them all as functions of x. They're all going to turn into x's. So all of those things are going to turn into x's. And what it's going to allow us to do is to use this rule to break apart this product. And so it's called ultraviolet voodoo because that's a way to remember this right-hand side. uv minus integral of v du, ultraviolet voodoo. So here's how we're going to do it. Now we can talk about why it works later once we get, the first thing you want to do is just to get used to the process. All right, so here we go. We've got this product. Division is the same thing as a product.
And keep the bottom definition.
Say that again?
The bottom definition of it, that one.
So this just says that if you have a definite integral, you would use the limits of integration, the normal way that you would with a definite integral. Okay, so here's what we're going to do. We're going to set up a little table. And what we have to do with ultraviolet voodoo is figure out what we are going to let u be and what we are going to let dv be. So we look at this whole integrand, including the dx, so all that stuff, and we need to break it apart into two pieces. That's what the u and the dv are. So the u and the dv, integral of u dv, we're going to turn this into a u and a dv. Now, when I look at this, there really isn't a lot of choices. I see that there's an x, I see two factors. So those two factors, I could put one with the u and one with the dv, or I could swap them, right? So I could put the x here and I could put the 1 over square root over here, or vice versa. Now, what you want to keep in mind is that when you're building your table here, to get to du, you take a derivative. From u, you take a derivative. To get to v from dv, you take an integral. So we want to think ahead. There's two rules of thumb. Pick the biggest piece, the most complicated piece, for dv that's easily integrable. Another rule of thumb, put something in u so that when you differentiate it, the power goes down, which simplifies things overall. So biggest piece with dv that's easily integrable, and whatever simplifies the best when you take a derivative for u. Like if you let u be the power of just the x to the 1, you take its derivative and you get 1. That simplifies it. And so if we did this, then we would have that. And the derivative of x is just 1. So if we do that, then we're going to come over here, and I'm going to rewrite this as x plus 1 to the negative 1/2. I'm going to pull it up to the numerator. So that would have to be the dv. The dx always goes with the dv because you have to integrate. So then we would have to integrate this, and this would be x plus 1 to the
1/2.
positive 1/2 divided by 1/2, put the 2 out in front. Reverse chain rule, just a 1, so we don't have to do anything. So this is probably the best option. We took the most complicated piece and integrated it. Square root of x plus 1 is more complicated than x. So we took the most complicated part and integrated it. And we took the factor that when differentiated reduced to just a 1.
Why take the most complicated piece and integrate it when usually differentiating something complicated is easier?
because it tends to simplify what's coming next best. If you can get rid of the most complicated piece by integrating, usually it's going to simplify this right-hand side. Almost always, if you take the largest or the most complicated piece that you can integrate, it's going to make the uv minus integral of v du the easiest, most of the time. So let's take a look now. Okay, so there's our recipe. That's our ultraviolet voodoo recipe. There's the voodoo. So now let's do the voodoo. So UV is this main diagonal, U times V. So it's going to be x times 2. I'll write that as 2x, and then the square root of x plus 1. So there's the UV. Minus the integral of the bottom row. So this is going to get to your question right there, Ari. If we took the most complicated thing and put it here, and then took its derivative and got something complicated, it's now going to be plugged into this integral. Which is why, if you can take something that gets simpler here, it's going to make this integral easier. And if this integral is easier than the original, keep on going. If this integral is more complicated than the original, you did it wrong. You've got to go switch your u and your dv. So let's see. So uv minus the integral of v du. So v du is the bottom row. So we're going to have 2 square root of x plus 1 times dx. And that integral is simpler than the original, so we're on the right track. So we can keep on trucking. So we're going to have 2x square root. So now we have to integrate this thing. We can factor out the 2. We can leave a space for the power rule. We're going to have x plus 1 raised to what power? 3/2 power? X plus 1 to the half. We add 1, we get 3/2. Then we have to multiply by 2/3 plus c. And so there is our answer. We would just combine the constant to make that a 4/3. So we'll make that a 4/3. And that's it. So that's how we use integration by parts, aka ultraviolet voodoo. So this is the traditional use of it. We have a product, and we're integrating a product by using integration by parts. Now, what's more interesting? Let's look at this. So we look at this trig function right, this inverse trig function. You know how to differentiate it, but you do not know how to integrate it. Ultraviolet voodoo works really well for some of these off-the-wall functions. Natural log of x, you do not know how to integrate that. Right? You know how to differentiate it, but you don't know how to integrate it. So check this out. Integration by parts works great for this, shockingly. So we need to pick a u and we need to pick a dv. We don't have a lot of choice. We can't put the inverse sign with dv because to get to v from dv you integrate, and we don't know the integral of inverse sign. So our only choice is inverse sign here, dx here. Do our little table. The integral of dv and dx gives v equals x. The derivative of inverse sine. 1 over blah, blah, blah dx. I'm going to put the dx in the numerator. Square root 1 minus x squared. So there is our recipe for this integration by parts. And then we use our trusty formula, ultraviolet voodoo. UV is x inverse sine of x minus the integral of v du. That's going to be x over the square root of 1 minus x squared dx. And what integration technique can we use for that? Substitution. If we let u equal 1 minus x squared, du will be minus 2x dx. And if we divide by negative 2, we have x dx isolated, which is right there, x dx. So this will be x inverse sine x minus integral. We said u is 1 minus x to the 2, so that's going to be u to the negative 1/2. X dx is du over negative 2. We'll factor out that negative 2 in a moment. So any questions up to that? So x inverse sine x, we're going to get a plus 1/2. We factor out that negative 2 in the denominator. So plus half. And then we integrate this power of u. We get u to the positive 1/2 divided by 1/2 plus c. And there is our antiderivative. Square root of u, what do we let u equal? 1 minus x squared plus c. Interesting. So now that's an antiderivative you'd never be expected to know. Is that me? Who is that? What was that? I heard something. Yeah, we. What's that? That is for the first one we did? Let me look at that right after class. Don't leave. You're not allowed to leave. I want to see that. Any questions on any of those steps? All right, we're going to do one more and then we'll be done. The antiderivative you've all been looking for. Ari?
You know, there's like 17-ish integration things. We need to memorize those.
Yeah. You need to know those things. That basic table. You should know most of them already. Natural log. Supernatural question. What's the antiderivative? You know the derivative. You calculated the derivative. Right? You know the derivative is 1 over x. The antiderivative. Once again, integration by parts is going to work great for this. And we're going to put the natural log with the u. We can't put it with the dv because then we have to integrate natural log, and we don't know how to. So we do the integral over here. Integral of dv is v. Integral of dx is x. Over here, we do the derivative, and we get 1 over x dx. So there is our recipe for this integration by parts. We go uv, x ln x, x ln x, uv, the main diagonal, minus the integral of what?
1.
1. The integral of the bottom row. X times 1 over x is 1. So we're going to integrate dx. And what's the integral of dx? Integral of dx? 1 what?
1x.
1x.
Oh, 1x.
1x, so just x. Just x. 1x.
Please don't write 1x.
1x. So there's the antiderivative you've been waiting for years. You've wanted to
It still has
know.
ln in it.
Of course it does. Just like the antiderivative for inverse sine has inverse sine in it. Yeah, so there is the antiderivative for natural log of x. X ln x minus x. If you want to confirm that that's the antiderivative, take the derivative of this, and you'll get ln x. The derivative of that is ln x. Yeah, that would make sense. Okay, so there are times where one iteration of integration by parts is not enough. And you may have to do 2 or 3. So when you've got a bunch of powers in here, you may have to do more. So
Will my math lab make us do it like 4 times?
not 4 times, but 2 or 3. 2 or 3. All right, let's stop there.
It's like an answer that's long.
Let's stop there. I will update the answer key for the exam. I'm super sorry about that. Some people got some free points.